Hello friends, today I will introduce some more important topics related to moments. You have all seen the definition of moments up till now. This is expectation of x to the power k, of course provided expectation is finite, otherwise it makes no sense. Now if I put k equal to 0, then obviously this is 1 and if I put k equal to 1, then m1 is expectation of x, which is the mean of the random variable. So this is what is said, that if the kth order moment is finite, then all the lower order moments are going to exist. So I am not proving that, it's enough for you to know it as of now. So if you have ex square finite, then obviously m0 is 1, but ex will be finite, and so on and so forth. There are distributions for which all the moments may not exist. For example, you know that Cauchy distribution is a distribution for which no moments exist. And if I take student T with 3 degree of freedom, then the mean is finite, variance is finite, but third or higher moments do not exist or are not finite. So now let us assume that ex square is finite. So such a random variable is said to be square integrable. In that case, you have this inequality that expectation of x square is less than equal to ex square. So consequently, if ex square is finite, then expectation of x is also finite. Something that I have already mentioned in much more generality, but this is one inequality which explains to you what happens. And in that case, since ex square is finite, we can define variance of x. So what is variance of x? You take x minus expectation of x, that is called the deviation from mean. It could be both positive and negative. Then you take the expectation of the square. So can you guess what will happen if this square is not there? Simply if we take the expectation of x minus expectation of x, so that will be obviously 0. So for any random variable or probability distribution, if you simply average the deviations from the mean, so the positive and the negative deviations will cancel out each other. Therefore we take the square average of the square deviations from the mean, so that everything is a non-negative. So it is a non-negative number, and on some further expansion, so a minus b whole square formula, you get this ex square minus expectation of x whole square. Now see, because of this inequality, you have this is a non-negative number. Now sometimes it is tempting to prove this using the definition of variance of x. Say that since variance of x is like this, and this is a non-negative number, so this proves this inequality. But that is not the case. We do not introduce the definition of variance first and then prove the inequality. Rather, we have to prove this inequality first and then define variance. Why? Because in the you are only told that ex square is finite. So how do you know that expectation of x is then finite? Because unless expectation of x is finite, x minus expectation of x makes no sense, right? So this we prove first, okay, and then we prove and then we can go for the definition of variance. Now this proof I am skipping here for the this course. Now this result is a generalization of this inequality called the Cauchy-Schwarz inequality. So if I have two square integrable random variable, that is both of them has finite variance, then expectation of the modulus x into y is dominated by the product of ex square and ey square. So you see that if I just take y equal to 1, constant 1, then obviously ey square, ey cube, everything is 1, and so you have this so here I have made a mistake in the Cauchy-Schwarz. This will be square. Sorry, square. Okay. So you see, this is how also you cross check things. So I have not written the square initially, so the square will come, because if you put y equal to 1, then this is the inequality you will get. And so now this proves that if ex and two square integrable random variables, then x into y, expectation of x into y will be finite. So since expectation of y is finite, so we now can define something called the covariance, which will be expectation of xy minus expectation of x into expectation of y. Now again, proof of this Cauchy-Schwarz inequality is easy when you have x and y to be both simple random variables. That is, when x and y both take finitely many values, and then you can prove this. So that I'm leaving perhaps as an exercise for you to think, but we can talk about that in later. So now once we have defined variance and covariance, we can define variance of the sum ax plus y, and in general we can talk about variance of a1x1 plus a2x2 plus akxk. They will be defined in the same way. So what happens, this is a square times variance of x plus variance of y plus twice a times covariance of xy. If you want a detailed proof, then it is very simple. You put instead of x ax plus y, and expectation of x plus y will be a plus expectation of x plus expectation of y. So you will have to put that there and then expand a minus b whole square formula. Now let us for a moment assume that not only the variance is finite, but the first four moments are finite. In that case, we could define something more, and that something is, we can define moment coefficient of skewness and moment coefficient of kurtosis. So now let us for a moment see what is variance. Variance is measuring the deviations, amount of deviations around the mean. So you see, if the reason I am squaring this, so that the positive and the negative deviations do not cancel out in each another. So on, if above or below the mean, if there are some very large or if there are values which are far away from the mean, either above or below, then that is going to make these squares large. And so average being sensitive to each and every value, so that expectation is also going to be large. Okay, so variance of x, okay, large indicates what? That some of the values of x are far away from the mean, either above or below. And variance of x equal to 0 will imply that expectation of this non-negative number, because this is a square, so expectation of this non-negative number equal to 0, and then the only interpretation is that that non-negative number is a constant with probability 1, so x is equal to expectation of x with probability 1. Now this is an extreme case, but in practice actually variance would be close to 0 or very large. If it is close to 0, that means the values of x above or below are all close to the mean. So there is very less, we call less dispersion or scatteredness around the mean. But large value of x, variance of x will imply some of the values of x are far away from the mean, above or below, so that is called high dispersion. So variance measures dispersion. Now we look at some other parameters called skewness and kurtosis. So we will try to understand them one by one in this lecture and the sequel of lectures. And so first of all, let us start with kurtosis. We will come to skewness in the other, let me do it in the other order. So coefficient of kurtosis, I am saying that it measures the tail heaviness of a distribution in compared to a normal distribution. So the important word here is in compared to a normal distribution, because I am taking normal distribution as the benchmark for comparisons of all other distribution. Now for normal distribution, I leave it as an exercise for you to verify that mu4 is 3 times the variance square. So you remember normal distribution has two parameters, like one is the mean, and another is the sigma, right? Recall. So what is for normal distribution, what is your mu2? What is this mu2? What is this mu2? This mu2 happens to be equal to sigma square. Okay. And your mu4 happens to be equal to 3 times sigma raised to the power 4 for. So this is the reason you get this coefficient equal to 3 for normal distribution. Now what is the idea of tail heaviness? If I look at the deviations from the mean, x minus expectation of x exceeding some number y is some arbitrary positive number. Now you know then there is an inequality called Chebyshev's inequality, which tells you that this will go to 0 as y is increased. That is true for any distribution that has and Chebyshev's inequality holds for distributions with finite variance. So that you can prove explicitly. But anyhow, for any distributions, even by using continuity theorem, you can prove that this will always go to 0. Now the question is how fast? Does it go to 0 faster than the normal distribution or at the same rate? So slower or faster. So heavy tailedness or a high value of kurtosis. So kurtosis will be more than 3. So kurtosis more than 3, that we call leptokurtic or heavier tail. So that happens when this goes to 0 at a slower rate than the normal distribution. So what does that mean? That means that suppose you are checking the probability 3. So x minus expectation of x greater than 3. Okay. Or 5. So if x happens to be n01 normal n01 random variable, if this mu is 0 and sigma is 1, then it will be mod expectation of x will be 0 and that will be mod x greater than 3. So that probability is very small. For normal distribution, that is 1 minus 0.9973. So for normal distribution, that probability is 1 minus 0.9973. So you see 0.0027. Now for if kurtosis is more than 3, then that probability would be bigger than. So here you will have more probability than 0.0027. For example, I leave it as an exercise. You can see what is that probability for a standard Cauchy distribution. Okay, so you take a Cauchy distribution with a 2 degree of freedom and find out what is, so I'll show you just here. So this is called R. It is a software for statistical computing. So here we can find everything. So I am finding probability into T distribution exceeding 3. Okay, degree of freedom is 2. Let us take a Cauchy distribution. 1 minus of that is, now it will be into 2 times, because here you are only looking at the probability for a random variable x following Cauchy distribution with 2 degree of freedom. What is the chance of exceeding 3? And to that you will also have to add the value falling below 3. So you see, you add these two. So what will be that? It will be 2 times of that. Now compare it with this probability. It is more than, it is almost more than what, 10 times, more than 20 times of this. So you see, Cauchy distribution has a heavier tail. So these probabilities would go to 0 at a much slower rate than the normal distribution. Or in other words, as kurtosis is high, and then these probabilities would be larger than that for normal distribution. And if kurtosis is less than 3, and if kurtosis is less than 3, then we call it platykurtic, and in that case these probabilities are much smaller than in compared to normal distribution. So one example is that if you look at uniform distributions.